example video on circuits. I'll probably make a couple and then I might find a couple more on the internet or something like that. Anyway, so this is a pretty simple example to begin with. So we're going to consider two 100 ohm resistors. We're going to think about them in parallel and in series. We'll go for a 24 volt battery, and we're going to ask what's the current through each resistor and what's basically the resistance, the total resistance. When they say equivalent resistance, they just mean total resistance, right? So what's the total resistance of each circuit? Okay, so here we kind of have a picture of those two situations. So first let's analyze the, oops, this is not the right one. This one. Here we go. So we've got them in parallel in this case, right? And them in series in this case. So I think we'll just do parallel first. So for part A, first we're supposed to think about how much current goes through each resistor, right? So we've got the total current coming out of the battery, and when they're in parallel, it kind of splits into part of it goes through this resistor and part of it goes through that resistor. So we can start out by just saying that current is conserved. So half of it goes through the first resistor and half of it goes through the second resistor. Okay? Then we can use Ohm's law and say that the current is voltage divided by resistance for each one of these cases. So that's pretty easy. So total current is voltage divided by resistance for each one of those cases. We're going to have this resistor value and this resistor value, right? This case we had the resistors are the same, but they definitely don't have to be the same. It wouldn't matter if they were the same or not. So in this case, they gave us what? I think they were 100 ohm resistors. Let's put that back on here. So in every one of these resistors in these problems is 100 ohms, just so we don't forget. It wouldn't really matter if they were the same or not, though, right? So anyway, voltage is not like V sub 1 and V sub 2 because the voltage across them is the same in a parallel circuit. When you have a parallel circuit like we talked about in class, hopefully, the voltage across both resistors is going to be the same voltage. That's one of the things that's beautiful about a parallelly constructed circuit. In a series circuit, that's not true, right? Like as soon as the voltage encounters significant resistance that's not negligible, it kind of has to split up so that energy is conserved. So in this case down here, we know that voltage is not going to be the same across each of those resistors. Voltage is going to be the sum of the two voltages across the resistors. But up here in the parallel circuit, it's the same across either resistor because you don't have to think about it like being split into two. And that's just because, like we said, that voltage is the same across any 2 points in a circuit as long as those 2 points are like at the same potential. So, okay. So anyway, I think that's the trickiest part of this whole thing, honestly. So the rest of it shouldn't be bad. So then we just plug in that this battery is 24 volts. We've got 100 ohms on that resistor and 24 volts on 100 ohms on that resistor. So plug those in your calculator, you get 0.24, you don't even need a calculator on this one, that's 100. So 0.24 amps for each resistor, so it makes sense, it's equal supply of current to each one for a total of, you guessed it, 0.48 amps. Better get my amps here. Okay, so I think the question also asked us what's the equivalent resistance of the circuit, so since these are parallel, you could go the total resistance, the equivalent resistance of the circuit, 1 over it is 1 over 100 plus 1 over 100 using multiple fraction things. So well, that's 2 over 100, right? Common denominator already, we got lucky. So 1 over it is 2 over 100. So in other words, the total resistance of the circuit is going to be 100 over 2, which is 50 ohms. So that's crazy. In parallel, remember you get the reduction in total resistance of from even less than what you started with one of them to begin with. So it's really nice. You could have also gotten this by thinking about like just the total circuit and the total voltage and current being supplied by the battery. So let's see if we get the same result if we think about the resistance as voltage divided by current from Ohm's law, the voltage supplied by the battery. Remember, we're ignoring internal resistance on all these problems, so we're just thinking it's perfect. There's no voltage drop, when of course in reality there would be. But anyway, 24 volts supplied by the battery, and then we said the current it's drawing, these two resistors are drawing is 0.48. If you divide that, I think you get, what do you know, 50 ohms. So you could get it either way on that one. Okay, so now let's go down here. I guess we'll do it in green. So pretend this was in green, just a different color. Let's do the same thing for the series circuit. So this time we said, since energy is conserved and voltage is a potential energy, we have the voltage is split into basically two pieces as you apply it to the resistors in this circuit. So now we can say that voltage, use Ohm's law, is going to be I R1 plus I R2. In this case, I is the same. So up here, voltage was the same in the parallel circuit. In the series circuit, I is the same. And that has to do with the same amount of charge flowing through the circuit. That's charge being conserved. So we've got two things here, energy being conserved and charge being conserved. Both big conservation laws coming into play. Anyway, we can factor that out, right, like this, and then see what we can get. So we're supposed to solve for I first, right? We know the R values and we know the voltage value, so I is now easy to do. It's going to be that 24 volts divided by R1 plus R2, isn't that 200? So it looks like we're going to get less current flowing through this circuit than when it was parallel. That's just like what we said in that last conceptual example we talked about. And you hopefully talked about it with me. Okay, so less current in the series than in the parallel. So that would mean that there'd be less power in the series than in the parallel. I mean, there's a trade-off. So if you wanted to expend less energy, going series might be a way to go. But if you wanted something really bright, this parallel is a better way to go. And there's other advantages we've talked about for parallel as well. But we still didn't finish the problem because we wanted the equivalent resistance. So the equivalent resistance for that is just going to be 1 plus the other. So a lot more resistance, and that correlates to our less current. If there's more resistance, there's going to be less current. So we get 200 ohms, and likewise, we could have done this kind of thing and gotten 200 ohms that way too. Okay, hope you found this useful. I'll post another example.